Hi again everyone, Chris Tisdell here again. Thanks for tuning in. In this video I'm going to continue my live streams of mathematics, and in particular I'm going to show you how to compute a special polynomial called a Maclaurin polynomial that approximates highly nonlinear functions. And the idea uses calculus, just basic derivatives and powers and factorials. So let me share my screen with you, and I can run you through an example that is designed to show you the main points. Okay, so suppose we have a function of x defined by root x minus 1, and here of course we're just restricting the x values to be, say, less than or equal to 1. So this is, we're just looking at the x values where f is defined. If that's our f, then compute the first 4 non-zero terms of the Maclaurin polynomial for f. So this is a special kind of polynomial named after a Scottish mathematician called Colin Maclaurin. Try saying that 10 times. Colin Maclaurin, Colin Maclaurin, Colin Maclaurin, Colin Maclaurin, Colin Maclaurin, Colin Maclaurin, Colin Maclaurin. You get the idea. Colin Maclaurin. Anyway. Maclaurin polynomials are important because they can be used to approximate functions near points. Okay, but how do we actually produce this special polynomial? Well, we just use calculus. So let me share my screen with you again, and I'll show you what's going on. All right, so let's get started. Actually, I think I might. Let me just move that. Oops. There. Okay. All right. That's better. Okay. So the Maclaurin polynomial, which I'll write as polyn of a function f of order. Now I'm going to talk about the order of a polynomial. I know that's a bit weird, but because you've got derivatives involved, order seems to make sense here. All right, so the Maclaurin polynomial of a function f of order n is the following. Okay, so I'm going to use this t sub n notation, and essentially there are 3 things going on here in this representation: differentiation, factorials, and powers. Differentiation, draw derivatives, factorials, and powers. Let me show you. Okay, so I've got the value of the function at x equals 0 plus the derivative at x equals 0 times x plus the second derivative at x equals 0 all over 2 factorial times x to the power 2. Okay. Plus the third order derivative of f at 0 all over 3 factorial times x to the power 3, and you just continue that. So you keep increasing the derivative by 1, increasing the power by 1, and increasing the factorial by 1 until you get up to the nth order derivative. Okay, so remember, by say 3 factorial, what we mean is 3 times 2 times 1. Okay, so 4 factorial would be 4 times 3 times 2 times 1. Okay, so that is an expression for the Taylor polynomial of a given function f, assuming, of course, all these derivatives are well defined. Okay, so here's our f. Let's compute this, and this for our given f, and then we just plug it into the formula. Okay. So let me take a new page and we can compute these derivatives. Now, the way I like to do it is just to form a little table and down the left-hand side you have the derivatives, and down the right-hand side you have the derivatives evaluated at x equals 0. So let me show you. All right, so remember, here's our f, and we have the following. All right, so let's write this square root as power 1/2. All right, so what we want to do there is evaluate this to get the first term of our polynomial, and evaluate that at x equals 0. Okay, so all right, so we put in x equals 0, we're going to get 1 to the power half, which is just 1. Okay, so the next thing we want is the derivative of f at x equals 0, okay, where that's our f. So we need to differentiate this with respect to x. Now we can do that just using this. Remember, it's just essentially an application of the chain rule, but there's a quicker way of doing it. All you need to do is bring the half to the front, bring the derivative of what's in the brackets to the front, and decrease the power by 1. Okay, so the half will come out the front, the -1 will come out the front, and you decrease the power by 1. So we're going to get -1/2 times this to the half minus 1, which is -1/2. Okay, so this evaluated at x equals 0, well, you're going to get -1/2 times 1, which is -1/2. Okay, let's keep on going. The next thing we want is the second order derivative evaluated at x equals 0. So let's keep on going and differentiate this. Same idea, bring the power to the front, multiply by the derivative of what's in the brackets, and decrease the power by 1. So I'm going to get -1/2 times -1/2 times -1. So that's going to give me -1/4. X minus 1 to the -1/2 minus 1, -3/2. Okay, and this evaluated at x equals 0 is going to be -1/4 times 1. Okay, and we've got 1, 2, 3 non-zero terms there. We want 4. So let's compute the third derivative. This should be the last one, as long as it's not 0. Again, power to the front, derivative of what's in the brackets to the front, decrease the power by 1. So I'm going to get -3/2 times -1/4. That'll be +3/8 times -1, -3/8, all to the -5/2. Evaluate that at x equals 0. That's going to be 1, and I get -3/8. Okay. Phew. Okay, a lot of differentiation. Okay, but it's quite mechanical. But now we can actually put the values down the right-hand column into our Maclaurin polynomial expression, and out will pop the Maclaurin polynomial. So let's do that. All right, so what's important here is this, this right-hand column. All right, so let's go back to our representation. That's going to be 1. This coefficient's going to be -1/2. This one here will be -1/4. And you just continue that on. All right, so we want t sub 3 in this case. All right, so let's have a look. It's f of 0, which is 1, plus f prime of 0 times x, so that's -1/2, so it'll be -1/2 x. All right, and then we've got this here, so f double dash of 0 over 2 factorial, so that'll just be 2. So the coefficient will be -1/4 times 1/2, which is -8 x squared. And the final one is down here, we've got the third derivative at 0 divided by 3 factorial. Now 3 factorial is 3 times 2 times 1, which is 6. So I've got negative 3/8 times a sixth. So you're going to get negative 1/16 x cubed. So there we go. There is our magical Taylor polynomial, Maclaurin polynomial for our f, where all these terms are non-zero, right? So if you wanted to write down the terms, because that's really what the question was asking us. Okay, so 1 negative half x, negative 1/8 x squared, negative 1/16 x cubed, okay? All right. So there we go. So we're delighted about that. Hooray! Okay, so reasonably methodical. Compute the derivatives, evaluate them, in this case at 0, and then just apply the formula for the Taylor polynomial. Now let me give you some geometrical insight into why these polynomials are important. Okay, so I've done a GeoGebra plot here, so let me share that with you. Okay, so here we go. The function, or the graph in blue, is the original f. So the graph is root x minus 1. Now what happens if I plot the Maclaurin polynomial that I've just computed? Have a look at that. That is, the red curve is 1 minus a half x minus an 8th x squared minus a 16th x cubed. Now, you can see here that in the vicinity of x equals 0, a little bit to the right and a little bit to the left, the curves match up very closely. Okay, but if I move over say here to negative 4, you can see there's a bit of distance between the red curve and the blue curve. So what does this suggest? It suggests that Maclaurin polynomials give a reasonable approximation as long as you are close to the point x equals 0. But as you move away from the point x equals 0, the curves on the may diverge, and therefore the approximation may not be as good. Okay? Okay, so Taylor polynomials give a reasonable approximation in the vicinity of x equals 0, and they can be computed using derivatives, powers, and factorials. Now, Maclaurin polynomials are special cases of Taylor polynomials where you're not working at 0, you can work at any point, say x equals 8. Now, in forthcoming videos, we are going to talk about infinite series, which is the next step up from this case. What happens if you keep on adding infinite numbers of bits to your polynomial? What happens? Okay, if you have any questions, any comments, any suggestions, I love getting feedback from you, so you can always post them in the comments section. Thanks for watching, everyone. Hope you enjoyed it. Bye. See you.